Welcome to Circuit Analysis. Let's continue the talk on the boost converter, and today we're going to talk about linearizing the circuit so we can do AC analysis. First we'll go over why we need to linearize the circuit for an AC analysis, and then talk about linearizing the PWM stage and the power stage, and talk about additional resources. So, why do we want to linearize the circuit? We want to linearize it so we can do an AC analysis. And why do we want an AC analysis? So we can make a Bode plot. Why do we want a Bode plot? Because that's the easiest way to assess the stability of our control loop. Now in introductory controls classes, they teach you how to convert your circuit to a state space, which is where you take a Laplace transform of it and represent it in a matrix format. And if we were going to do this power converter by hand, we would then take the state space for the converter with the switch on and the switch off. So we'd have two separate state spaces. And we do what's called a state space average of those two states proportional to the converter's current duty cycle. And the thing is, PSPICE does this first part, the converting to the frequency, but it doesn't have a way to do this state space averaging part. And that is essentially why we have to create a linearized model of our circuit. So remember, here is the boost converter, and the nonlinear parts that we're worried about are this switch here and this diode right here. And if we were going to draw a box around what we need to linearize, it would look something like this. So we have the switch and the diode is one block, but also this control chip. So what we need to do is have a signal coming back from the output feedback path that is here, and that is going into the linearized block, and then out of the linearized block we're going to either have a voltage or a current that's going to be the output of the converter. To determine if the output of our linear block should be a voltage or a current, we look at the next component in the circuit. So since the next component here is a capacitor, we want the output of the linear block to be a current, because if it was a voltage, you would be essentially discounting this whole part. You'd just be fixing the voltage on here. But if the output is a current, then this is still an active part in our circuit, because we know that the output capacitor has a large effect on the Bode plot and the frequency response. But because we're essentially turning this whole thing into a voltage controlled current source, we're going to be pretty much getting rid of this inductor here, and we're going to have to wrap that into our linear model as well. So here we are in PSPICE, and we're just going to make a super simple, not super accurate linearization of this boost converter just to nail down the concept, and then I'll give you some resources if you want to look up how to make more complicated, more accurate linearized models for different types of converters in the future. But basically what we have is this feedback voltage coming here, and we just want to turn this feedback signal into a voltage controlled current source. So the voltage control is the feedback and the current source will be the output of the converter. But what you need to think about here with this PWM chip is what is the voltage control. And first you think it's this feedback line, but it turns out that this feedback line does not actually change its voltage in steady state because of this op amp with this fixed reference to 2.5 volts. So the feedback voltage that moves that we actually want to look at is this line on the output of this op amp. And that's the one that's going to be linearly proportional to the duty cycle. And luckily that's brought out here as this comp pin of this chip. So we're actually going to be adjusting the comp pin and seeing how that affects the duty cycle. And then you could linearize this whole thing at once, or you can do it in 2 blocks. So sometimes I like to do 2 blocks where first you just linearize this chip to a duty cycle, and then after that you have another block that converts the duty cycle that is now represented as a DC voltage between 0 and 1 instead of an actual pulsed duty cycle. It's a mathematical duty cycle, and that gets converted to an output current. So to check out the ratios between this voltage here on this comp pin and the duty cycle and the output current, we're going to copy this source here and press H to flip it horizontally. W for wire, rename it VC for control voltage, and let's just give it, this is going to be between 0 and 5 volts, so we'll just give it a 4 volts right now. And we're going to go into our analysis here and set up a parametric sweep. We just want 10 points or so, so we'll change this to a voltage source. It's going to be VC, and then down here we'll do linear 0 to 5 at half volt increments. Let's apply that. Oh, I forgot to mention this is set to run for 3 milliseconds, and we're starting saving time after 2 milliseconds. Okay, let's save everything, and we'll run this. Here's our results. So what we really want is the 3 parameters of interest: this comp voltage, the duty cycle, and this output current. So we've got the comp here at the top, or we can just delete this plot. We've got the comp, the duty cycle, and then this one here is IL, but we actually want this output current here. And then this one here is the output voltage, but we can delete that for now. We can save this setup. So we're going to want to add some measurements here. View measurement results. And the first one we want is just the y at last x of v comp. That'll give us, because these are all DC, so that'll give us the DC value of this v comp. And the next one is the duty cycle. So they have a duty cycle formula of VD, because this is the actual switching duty cycle. So that gives us the duty cycle here between 0 and 1. And then the last one is this current here, which is looking pretty funky. So if we zoom in, you can see that one of these waveforms didn't work very well. This blue one here, which is 1, 2, 3, it's the third one over. So this is 0, this is 0.5 volts, and this is 1 volt. So we might just get rid of that one, but we won't worry about it for now. So for this output current, we want the average. Let's insert a new waveform, and we're looking for average X. Here we're going to put V, now I, D1. Yep, we forgot to give it an averaging time step, so we're going to do 10 microseconds. And now it's probably a little bit hard to see. We can delete this old one, and now we just have this averaged. So there's this really funky spike here in the beginning that's killing it for some reason. I guess we can just double click on this and do user defined, put 0 to 5 or something. Maybe 0 to 10, give us a better view. So all this stuff here is around 4 maybe. We can increase this to give it more averaging. So there, that's a lot smoother. We really want a really solid average, so let's just increase the average again. And if we zoom out, now it gets pretty smooth out here, so you can see the averaging is sort of a moving average. And we can copy that, add it to a formula down here, so we'll do y at last x again. Put that average, that'll just get this last point here, which is pretty averaged out. I think a spreadsheet's the way to go. So let's copy this section right here, paste it in the spreadsheet. We'll copy it again, and we're going to transpose it. So now we have everything in these columns, and we can get a new column here, call it VC, and this is 0.51. You can extend that down. This is our control voltage. And these guys here, this is our duty cycle. This is our output current. And this is our control voltage. And now the first thing to notice is that these control voltages don't match these. Yep. So this guy here is not connected to ground. So we need to copy this ground node over here to force this voltage here to be the actual control voltage. And we'll run that again. All right, we'll copy and paste it again. Transpose, and this time it looks like our control voltage does match the set point, so that's good. To clean this guy up, we can use this left formula here. We can do the left of the length minus 1. And that'll get rid of this M here. But with that, we're going to have to do the value because it's text. And we can also multiply it. Let's see, we'll divide it by 1,000 to convert it to volts because it was millivolts. And we can replace that. And this one here, we can get both of these. Format the cell, and we'll just do 3 decimal places. These first two didn't really work because, well, it says milli here on these guys, but that's definitely incorrect because 0 is not a full duty cycle. So I think if we make these two 0, that's a little better. This point here is probably pretty inaccurate. This probably really makes sense because it has a little offset voltage before it actually starts switching. So it's probably below 1 volt. It doesn't really switch much anyway. And these guys right here aren't really looking very accurate either. Because see, this is bigger than this. And then it starts here is when they actually start increasing each time. So I'm going to call this one not really any good, 2. And we'll just say it just starts right here. So I'll make that one 0 as well. And this output currents here don't look too legit either. With 0 duty cycle, we want 0 output current. And you can see that these are all the same here. So we'll just put 0, 0, 0. And now we have right here this lookup table. Once you get a 1 volt control voltage, still 0. When you get to 1.5, that's when it starts to get up to 2 amps. So you have a pretty steep ramp here between 1 volt and 1.5. It gets you up to 2 amps output. So to implement this lookup table and linearize the circuit, first let's we'll click on the project here and then go save project as and give it a new name. So we can save the old one. We'll just call this linear 1. That way we have our old circuit saved just in case we want to go back to it. And we're going to go P to place a part. So we want this ABM, analog behavioral model. If you don't have that in here, click this plus and here it is, ABM, add it. And then we're going to do, let's just do, there's a lot of different ways to make a table. In PSPICE, you just write table and a voltage source. But this one here is sort of a graphic representation of that. And this is a voltage to a voltage. So then after this, we're going to have to place PSPICE component and do sources. We want a controlled source. So it's a voltage controlled current source here. So we can use this lookup table and then put that into this to convert it to a current source. So to wire that up, we can just put a ground right here and wire this one straight into here. And the input is going to be from this feedback. We'll get rid of all this stuff and we'll get rid of this and just make this pump current from ground straight to the output. Now at this point we're not even using the input voltage, so this is a pretty bad linearized model. But now we can implement this lookup table here, copy it over to here. You can see in the properties here, they've got these rows and they're just being put into this PSPICE template where it's just got this table function here in this voltage source. And it's a controlled voltage source, or a voltage source with an equation. And then in here they just have row 1, row 2, row 3, row 4, and row 5. But it stops at row 5. So we actually want to make, let's see, we ended up 3 volts. So we want 3.5, 4, 4.5, 5. We want 4 more of these. So we're going to have to copy this little section here. 1, 2, 3, 4. We have to make 4 more rows. And we'll have to add properties down here for rows 6, 7, 8, 9 as well. So there, I think we've got it. We've got these PSPICE template row variables updated here, and then we have more rows added here that we can copy these values into. I'll just copy and paste these ones for now. Oops, and I've put the labels on this, so. So there is our linearization with a lookup table. And we have our gain with a voltage to current conversion of 1 right here. So now let's go back to here, get rid of this parametric sweep, and we'll just start this at 0 to 3 milliseconds and run this and see what it looks like. So it took a while and it gave this whole waveform, and all these waveforms came back that we deleted. So I don't know what it's doing. vcomp vd is showing an actual duty cycle. So it looks kind of funky. I think I need to just turn the whole program off and restart it. So this time it started up. It says PSPICE for TI, which is some kind of a package I installed. But now my whole interface is in the dark theme, so I don't know what's going on. I'm just going to exit this again and try and start it fresh. Okay, we're back. This time when I ran it, it says 2 out of 3 traces non-existent, and it loaded immediately. So it looks like it's working again. So whenever it stops making any sense, I guess just restart the whole program is the moral. Now we want to add in here a couple of plots. I want to look at the output voltage. We want to look at the feedback here. We forgot to label, so let's label that. Press N for net and then feedback. So we can do an insert here and do V feedback. You'll have to zoom out on this stuff. So this is not super great here. You can see that the voltage is decaying pretty fast. So it's definitely not a steady state, legit linear model. But we have it fixed here at the 70 volts output operating point by our initial condition on this capacitor, which we could double click and display just to make it a little more clear. So this is the initial condition here, 70 volts. And so now if we want to turn this into a Bode plot, we need to add a AC source, and the way we do that is put that at the beginning of the feedback path. So this is the feedback path right here. This is the beginning here, and we might as well just get rid of this extra stuff here, make it a little simpler. We'll go place, PSPICE component, source, and we want a voltage source, AC. And it doesn't really matter the polarity, but I like to think of it as the negative is kind of here and it's injecting the signal down this way into the feedback path. So we'll just put it this direction with the positive facing down. And I'm going to rename this VAC. W for wire. Now that we have this in here, we need these nodes to be named. So we'll call this feedback, and this one we'll change to feedback 2. Now we got to make a new simulation profile. Let's call this one AC. And this is going to be, instead of a time domain transient, an AC sweep noise. And we want to go from maybe 100 hertz to, let's do 1 megahertz. And points per decade, we'll do 50. So that's it. We can pretty much run that. Now we have our frequency response here. So we're going to insert and do a waveform. First thing we want is the gain of the Bode plot. So we're going to do dB and then V. And this is a ratio. So it's that feedback signal, FB, and it's divided by V of the output. And yep, I did that backwards. So it's the output divided by the feedback. There we go. That looks a little better. So your gain should be decreasing with frequency. So now the next one, we can just copy this one here, insert another one, and for the phase, instead of dB, we'll just put a P for phase. And there it is. So this is pretty not making a lot of sense here. The phase is just dropping down like this. It's below the gain for all the frequencies we're looking at. So this is not a legit control system. And what you might have figured out already here is that the main reason is because we've kind of thrown out our controller. See, we got rid of this whole control chip right here, which along with the reference and this compensation that we put in. So we linearized it right here at the output, but we need to add this op amp back in with the reference and this little network here. So to add that back in, we need an op amp, and let's just do the analog library, and we'll try this op amp here. Press O. And this is just a controlled source, so it's super ideal op amp. We'll give it a reference of 2.5 volts and do that compensation, just like in the other schematic. Now that we've got the op amp back, let's run it in the time domain again. So we're going back to this linear project here, and under this PSPICE resources, we have the two different simulation profiles. So we'll right click and we'll activate the transient one. Run that again, see if that works. So that one looks a little bit interesting, but it's not exactly reaching steady state at the 75 volts, and this feedback is really crazy. The feedback is showing 75 volts. That's because this here should actually be feedback 2 now, although I think we forgot to include that, so we're going to have to do feedback 2, put that one here, run that again, and this guy here should be feedback 2 now. So let's try 10 milliseconds on the simulation. So we can see here it does stabilize here back to 75, 76 volts or so. But it has a pretty crazy transient. This guy, I don't know why the auto is not really working here. So let's put 0 volts to 5 volts. And now we can see this one here is approaching 2.5 volts here. So that's doing what it should with the op amp tracking this 2.5 volt reference. So having this transient not be exactly at steady state when it's starting, that means that the DC bias operating point is not going to work out perfectly for our AC analysis. But let's just try it anyway and see what happens. So we'll make this active again. So we're doing the AC analysis, and we'll run that. We're back here, and we should have saved the waveform because forgot to do this thing that you have to do every time. Go to the probe window and do the last plot. But anyway, we'll insert it again. So this is looking better. We got the phase starting up here. It should start at 180 degrees and decrease down, and we're looking at where things cross 0. Now this gain is not making a lot of sense here because it's below 0 starting out, and the phase never drops down. So there's definitely something wrong with our circuit, and I'm going to guess that's our operating point. So if we look back here, if we click on the voltages here, we can see this one here is 4 volts out here. This is 15 volts. So we've got 15 volts coming out of our op amp, and that's way off our table. So this thing's just totally railed high. So that's not a steady state value at all. So we're going to have to fiddle around with this circuit and try and get it into a position with our initial conditions where it's calculating a steady state bias point as its initial guess, which should make this output here in this table range, so maybe 3 or 4 volts. So to do this, we want to get back to the transient analysis, and then I think we'll want to start by just checking all of our initial conditions. So this guy here has no initial conditions. This guy here, I want to see what happens if we just get rid of this one altogether. So let's delete this 70 volt initial condition and see if this thing will still regulate. Looks like it's decided here to start at 0. That's not what we want. What we want is to have everything start out steady state in this transient, so just everything flat lines. So I think the easiest way to get this in the operating state that we want is going to be to just figure out what the steady state voltage is across this capacitor and this capacitor, because those are the only two time varying components in our circuit, and just set an initial condition to that value. So let's check it out. So I always got to check your polarity. So pin 1 is on this side. We do a differential probe across here. Then we get this one. We can get rid of this average thing here. Here at the end, it's reaching a steady state, so we can use this little probe tool from up here and look down here and see if you right click, you get another one. So that's the delta. These are both pretty much the same right now. So these are the values here. V out 77.658. And then this capacitor is 1.3501. So let's see. 1.3475. I don't know, something like that. We'll just use this one, 1.3475. It's still got a little funk to it. It looks like now this one is saying 77.5 is the output almost exactly. So let's try that. 77.5. See if that makes it any better. So now see we're honing in on the steady state point. So this one's 77.5, but now this feedback 2 is looking a little bit more like 1.3468. So let's try that. 1.3468. All right. So now these waveforms still look a little crazy, but you can see the numbers here are super tiny. So we're pretty much at the steady state now. It's time to make the AC active and see what we get here. So there, that looks more like a Bode plot. So we have the gain starting at positive here and crossing down over 0. So this is the gain bandwidth right here. It's pretty low. It's below a kilohertz, and then the phase is going off over here. The phase should cross down over 0, and we're not really seeing that. That's probably because it's such a simple circuit and we don't have like a realistic op amp, and some of those things we can try adding a couple things to make it a little bit better on the phase. First, let's just swap this out for a different op amp, because that one has like a totally flat response. Normally the op amp would drop off at higher frequencies with its gain bandwidth product. Let's try a op amp library here. So I don't know why this op amp library isn't working. Seems to be responding, but see, none of these libraries are doing anything. Uh-oh. Unable to load package. All right, let's try this again. Unable to load package. Okay. Time for another reboot. All right, we're back. It's working again now. So op amp package here, and then I'm just going to look for an op 27. I'll type op here. Here's a 27. That's an old op amp. Put it right there. So this one we're going to have to attach some power to. So we'll just use this one, and let's put this one to ground. Change this one. I'll make it 15 volts or so. See what that does. So now it's starting to make it come back down here at higher frequency. We can extend the simulation a little bit to see what that looks like. 100 meg, and so that now you can see it's rolling off here at higher frequencies. It's really high though, up 10 megahertz, 1 megahertz. So a couple other things we can add to make this slightly more realistic is we can put, I don't think this is actually going to help this, but there should be some ESR, which is actually a big part of the Bode plot on the output filter capacitor. So if we put that in, let's make it like 50 milliohms. And if we run that, let's see, okay, so that changed it a fair amount. It actually didn't really help this part here, but it brought it down on the lower frequencies. And Then the other thing with a standard compensator is we might want to throw another capacitor in here. That'd be like a roll-off capacitor to help the gain roll off a little and bring down the phase at higher frequencies. So if we make this one maybe 100 pico or something, just doing random stuff for right now. Get rid of this initial condition. Click on here, right click. So there it is, Bode plot. It's probably not going to match the actual hardware real well, but this is just to illustrate the concept, so hopefully that makes a little bit of sense. If you want to get more into this stuff, these are the people you want to be searching for. These guys at the top have books and publications, some of the pioneers of these kind of models, and then this is just a couple of YouTubers that I've enjoyed watching video format about. That's easier sometimes. So check it out. I think next time I'm going to get into tickle scripting with PSPICE. If you'd like me to go into more detail in the future and get really into the guts of some of the more legit models by some of these guys up here for linearizing different types of converters, let me know in the comments and I can make that a priority. Otherwise, that's it for today. Thanks for watching, and I'll see you next time.